do have a question on the data.
Yes.
So in Gregor's note, Gregor mentioned that we probably need to do things a little bit differently in terms of how we're making the data available. So I take it it doesn't suffice to just link to the original source, or did I not get that correctly? Do we need to in essence, have a copy of the data and not just reference a particular URL where we got the data
from? Should I comment?
Yeah, you can comment, yes. Okay.
So there are two ways on how to do the project. One is with Python on your local machine. If you have a CUDA card or something like this that you want to use. The other one is using Google Colab. In both cases, the data must be locally on the machine, because if you don't have it locally on your machine, it will fetch it and make the fetch process slow. And depending on how big the data is, that will be slowing down your calculation, or you may be charged differently in Google Colab, for example. So the one thing that you can do in Google Colab, you can mount the content directory in Google Colab via your Google Drive, but then you use your notebook to use the Cloud Mesh shell.download function to download the data into this content. Now, the way how the download function is designed is that if the file is present, we don't check if the checksum is correct or anything is correct, but if the file name is there, it doesn't download it again. But if the file name is not there, it will download it. Now, this makes it possible, and I will be posting another post this week to add to those who are using Google Colab books a link within the Colab, so that your notebook can be executed by someone else. Naturally, that someone else does not have access to your data. So therefore, they will not be able to run it. However, if you have the download function in your notebook, they will be able to run it, because they will find, okay, in that directory, I can't find that particular data set, and it's not there. One of the things that you need to be identifying is how do you componentize the location of your mounted directory in Google Colab. So what likely is going to be happening is this is on the topmost line, or is in the directly after the imports. You have basically, oh, this is my Colab directory, and this is how I'm mounting my my Google Drive into my notebook, and then the person, the grader, will be able to replace it with their own environment. So that's what the issue is. The other issue I pointed out is we need to know how long your Google Colab notebook actually does run. If you, for example, have your Colab book running for a week, and we have 2 days time to grade your Google Colab, and we start this Colab 2 days before, we have no reasonable chance of grading this, right? Or replicating that thing. So you need to be making sure that in your notebook or in your report, you write, okay, my code runs like this long under these conditions. So these are the two major issues that we typically have. And I said, I will be providing you with a link on how do you add this to your Google Colab book, so that when another person clicks on it, that link, that Colab notebook will be replicated in someone else's environment.
Thanks, that's really helpful.
Any other questions other than Baikun's? All right, so Baikun is asking a question about time series, and I will indirectly address it by discussing a more complex time series, the one from earthquakes, which I'm working on. I assume you can see my thing which says earthquakes and deep learning.
Yes.
Yes.
All right. All right, let's just leave it at this. I can't find the annotation button. Okay, so we actually did this right at the beginning, but I just repeat this couple of introductory slides. And the earthquake problem has not a huge number, but a reasonable amount of data. And it's actually available from 1950 to 2019. There's more data starting in 1990. And for each earthquake, you have a magnitude, a position, a depth, and a time. And that's what we'll come back to later. And a pretty interesting, important feature of earthquakes is that, fortunately, the number of large earthquakes is small. So there's the so-called Gutenberg-Richter law, which says that if you increase the magnitude of the earthquake by 3, the number of earthquakes goes down by a factor of 1,000. So there are lots of small earthquakes and a few large ones. And that's recorded at the bottom here. We have 900,000 magnitude less than 2.5 per year. And for magnitudes 8 or bigger, it's 1 every 5 or 10 years. In tandem with this feature that earthquakes there are only a few large earthquakes is the sort of physics of the problem. Namely, the magnitude is the logarithm of the energy release. So if you have a magnitude 3 and a magnitude 6, they differ in energy by 10 to the 3 times 1.5, so 10 to the 4.5 over a factor of, whatever that is. That's a factor of 30,000. So there's a huge difference in energy. And that we'll come back to. And I mentioned this difference when you look at the world of earthquakes, which I've worked in various ways for some time. There are 2 parts of earthquake work. One in which you hear about more is actually called earthquake engineering. That is predicting the damage once the earthquake happens. That is computationally intense, but reasonably straightforward because it's physics. With known physics, and we can, for a given earthquake, we can calculate what happens to the building as it oscillates, and the various parts of the building may or may not survive. So that earthquake engineering doesn't have super challenges other than needing lots of computers and highly non-trivial solution techniques. However, what we're trying to do here is sometimes called earthquake science, which is forecasting or understanding the occurrences of earthquakes. And earthquakes happen because you have these plates sitting next to each other underneath you. Well, not here, there's only a few earthquakes here, but if you live in Southern California, where I used to live, those quakes are rubbing around and moving every day. but they're not actually moving every day. They just move every now and then. And if you think about the laws of friction, when you have two things which are sort of up against each other, they only slip, and the slipping of these faults is what causes the earthquake. They only slip every now and then, and in the physics language, that's called a phase transition. And so it is not calculable as solving equations, because the phase transition happens in a rather unpredictable fashion. That's true whether it's ice melting and freezing and things, or in earthquakes. All phase transitions are much harder to study. So the only chance which has been actually pursued for a long time, even before AI and deep learning became popular, was to try to look at patterns. Namely, probably for thousands of years, people have noted patterns that could forecast an earthquake. It's mentioned here that dogs barking. There are other patterns such as water leaking out of the faults and things like that. So there's some hope that there is a structure of activity on the Earth, which may be other quakes, because remember we have millions of quakes happening around the world. That those quakes maybe have a pattern which can forecast a big event. So before we go back to that, let's just make a few remarks about time series. So there are lots and lots of problems which end up being thought of as time series. And at least I think most of them can be thought of as a set of events. In the case of the earthquake, the event is the quake. In the problem, say, which Baikun has, which has various activities such as using coal or stocking natural gas. The event is the fact that there is a certain amount of gas stored at a particular time in a particular place. Anyway, so a huge number of problems are determined either by events or by cumulative records which happen as a function of time. His problem is more like the COVID problem, where actually you don't see events. We are not told when everybody gets COVID. What you're told is that, haha, today 36,000 people were diagnosed with COVID. You don't get down to the detail of the 36,000 tests which returned positive results that day. So sometimes you only see the cumulative daily or weekly, or in the case of Baikun, monthly data, and sometimes you see the events. For earthquakes, you see the events. And these events are functions of space and time. In the case of, say, Baikun's data or COVID data, it's actually binned by city. He has energy resource data as a function of cities in Korea. When we studied COVID, we had number of cases as a function actually of counties, not of cities. But that's essentially, in some cases, cities. And New York County is dominated by New York City and so on. And Cook County is dominated by Chicago and so on. Marion County will be in Indianapolis. Okay. So when the standard time series which you see in industry is audio, and that audio is certainly events. When I speak, I'm issuing, my tongue is chopping around and issuing audio waves into the world, and what you see is what happens when those audio waves hit somewhere, and you get an audio signal, which is what you record as typically you wouldn't record it continuously, but you'll just record it at discrete times. So even when, as in earthquakes, there are events, the processing methods are actually much easier to think of if you don't think of events, but you just think of, you divide the world and time, you divide time into bins. In the case of earthquakes, those bins could be minutes, days, weeks, years, and then you accumulate everything that happened in that bin into a single measurement. As over COVID, you get that automatically because every county only reports the daily data. And we also have a choice of space. In the case of Baikun's data, which is Korean cities, the space bin is given to them by the data. Each city has separate data. In the case of earthquakes, actually, that's not true. You're given it as a function of space, so you have to not only chop up time into bins, you have to chop up space into bins, and you accumulate, therefore, in the case of earthquakes, all that happened in the particular space bin and the particular time bin. We chose a time bin of 1 day and a space bin of 11 kilometers on the side. That 11 kilometers was partly a practical choice and partly an intuition from the physicists who study earthquakes as to what a significant distance was. Namely, you don't even measure the location of the earthquake that accurately, super accurately always. And also, there is going to be a spatial region that a single earthquake is actually spread over. It doesn't happen just at one space point. It is centered at a space point, but has activity across quite a lot of non-zero spatial domain. And so we chose 11 kilometers as that spatial distance after talking to the experts in the field. And that's an important, when you're doing this work, it's good to have an expert, like in the case of gas resources, it's good to have an energy expert, a resource expert who will tell you what time interval is significant. Well, this is just an example of COVID, where actually if you go to at least one, either the Johns Hopkins or the Worldometer's website, you actually do get cumulative results. Although you don't get single events, but they add the events into the accumulated for each day, so it actually increases as a function of time. This was from an earlier time in the year when it was actually somewhat more there was somewhat more cases than right now. Not a lot more, but somewhat more. I think they're now more like 60,000 cases a day. And the number of fatalities is more like 800. Anyway, so, but the only thing that's recorded permanently is that, at least as far as we're concerned, is the total at the end of the day. And that's what you'd use. And this gives you these plots you see here. So this was from November 2020. So I've already pointed this out. COVID is naturally binned, not much, and so is Baikun's data. Earthquakes can be binned and are not binned naturally, but you can bin it. And there is some at least natural choice of a spatial dimension, because that comes from the physics of earthquakes. And the time bin probably is not so trivial. We had to experiment with several time bins. We actually ended up with 2 weeks as our time bin. Another study I did of earthquakes used 4 weeks. So it's there is no absolute truth here. It's partly computer time. If you do these analysis with daily data for earthquakes, and as you have 70 years of data, daily data for 70 years is a lot of data, and you can't run it on CoLab in an efficient fashion. And of course, time series are also sequences, and typically this is the methods used in industry are called sequence-to-sequence mapping methods, because you have one sequence, the audio signal, and then you want to map it from audio to text or from English to French, or what have you. So this is called a sequence-to-sequence map, is audio to text, or English to French. Forecast you see in the when you start typing, at least when I type in Gmail, it tries to tell me what to type in the future. It is doing a sequence to future mapping to suggest that this word is typically followed by some other word. Now, again, in science, in earthquakes, we're actually not terribly interested in sequence to sequence. We're interested in sequence to future. We need to know when the next big earthquake is in a particular region. When I did hydrology with these methods, we wanted to actually do both sequence to future, find out what the rainfall is next year, or we wanted to do some mapping of daily rainfall and temperature to plant growth. That is a sequence to sequence mapping. So another example from physics is force equals mass times acceleration. That is a sequence to future theory, Newton's laws, which is a forecast. And election polling is typically a forecast, or is sometimes as an opinion. You might be trying to map this data into an opinion as to whether the possible infrastructure bill that Biden proposed is popular or unpopular. But I don't think polling is actually done as time series. It probably should be, but it isn't. Well, this just points out that deep learning, as you can view as a sort of new alternative to having theories. Newton's law, traditionally force equals mass times acceleration. After you discretize, remember you have to, I pointed out for time series, you had a bin, that's called delta t for Newton's law. It's the time step. You move into the future, and you can use Newton's law to predict from the current position the future velocity, position, and acceleration. And so, so actually what we're doing in all these things is pretty interesting. We're trying to find operators that take us from where we are to where we want to go. And that's a reasonably deep idea, because at least when I started off in science, we weren't able to we didn't think of statistical methods as a way to take us into the future very reliably, very seriously. We just used Newton's laws or equivalent. But now I would say you can use deep learning operators to predict the future in a non-trivial fashion. And so, well, this just points out, if you look mathematically at how the different formulation of differential equations for Newton's laws, the Newton's law says the new values at a later time are the operator times the previous values. And if you look at deep learning inference, it actually has the same structure. You have a differential operator, the neural net, which you've trained, and you say the new values are the neural net times the previous values. And so in some sense, deep learning has either replaced or augmented or extended, maybe is a better statement, at Newton's laws. It's pretty different in structure from Newton's laws, because you can, if you write down a time series, deep learning operator can have many millions or probably billions of parameters, but the ones I use have millions of parameters. And Newton's laws only has a few parameters, just determined by whatever the equation is, the potential and the mass and things. All right, so now let's see what we would do when we wanted to take a world which had time series and try to address it with deep learning. So let's, for the rest of the slides, we will assume the data is a time series. Well, here is something which already is we can address, which is important, which is what is the data? Well, in the case of earthquakes, there's some obvious data, which is after we've done the binning, we can look at the sum of the magnitudes which are in that bin. Well, actually, it's not quite obvious how we add the magnitudes together. We'll come back to that, because if you sum the magnitudes, that's probably not the right thing to do. And I'll explain that a little later on. But for some things, like Baikun, I think, had temperature as one of the things he had, average monthly temperature. Well, that's certainly a reasonable input data. So that points out that when you look at your input, you have static input and dynamic input. Static is independent of time, and dynamic is time dependent. And you should consider both of those variables. When I'm doing Newton's law, the mass and the parameters of the potential are static, whereas the position, velocity, and acceleration is dynamic. You also have a sort of subtlety. You can sometimes get data on different time scales. I think Baikun said that all this data was monthly. But in principle, you could solve problems where some of the data was daily and some was monthly. Here is a very important choice. Namely, if you have a feature X, like temperature or magnitude of earthquake, as far as deep learning is concerned, you can replace X by any function f of X. And that is a pretty important step which you will want to use in many cases. And because there's nothing in deep learning that tells you what function of X is. I think I will explore this a little more in a later slide. But it's most dramatic for earthquakes. I have a slide which shows this plotted out. Namely, if you just take the data as it's given, you just have a magnitude. But let's suppose we had two magnitude 3 events. I add them together, I get 6. Is that the same thing as a single event of magnitude 6? I don't think so, because two magnitude 3s will hardly do anything noticeable, whereas a magnitude 6 is likely to be noticeable. And that's because actually the magnitude 6 is 10 to the 4.5, 30,000 times more energy than the magnitude 3. So really the comparison is actually 30,000 for magnitude 6 versus 2 for two magnitude 3 earthquakes. So whether if you added magnitudes or added energy, you'll get vastly different answers. And we will come back to that because it's not obvious what the answer is. And different problems will have different Fs. I think you should, in the case of traditional machine learning, there are things like kernel functions. Well, this is, if you like, a kernel function, which is implicit in any formulation of deep learning because it doesn't tell you what your input feature is. So the next thing is, what is the output? Well, the output has the same X goes to f of X issue. And typically the output, I told you there was sequence to sequence where the output was a different observable at the same time. But we're going to focus on the forecasting model, which I think is what Baikun wanted, which is what's going to happen at a later time. And here is sort of interesting. Deep learning is pretty peculiar in that you can do anything. Namely, if you did have data on dogs barking across the world, you could try to train a deep learning network on number of barks per time, which would then predict the value of the IBM stock or the number of earthquakes in the following year in Southern California. Now, and again, I pointed out you could also take data on daily rainfall and try to predict stock prices from that. The deep learning, as you formulate it, that doesn't care. It just needs that you have a series, and that series has a so-called prediction, and you tell it what the prediction is. You train the model to give you that prediction. you will obviously get very little out if what you're predicting is totally uncorrelated or nothing to do with what your input is, but still the deep learning model will run, just presumably won't give you very useful results. So you have to be sensible, but you can be pretty broadly based. And so with earthquakes, we have a choice, as we see, of actually what the function f is, and also about what the prediction is. And you can use a prediction, which is there an earthquake tomorrow? Or you can do something which is probably more useful. Is there an earthquake in the next few years? Because what you really care about for earthquakes is the probability of a large earthquake in the modestly future, because it is possibly easier to predict. Usually earthquake forecasting is predicting is probability of a significant event. Another problem which you have to decide is exactly the loss function is almost always least squares, the sum of the prediction minus the observed, the predicted value versus the observed value, but also you're never quite certain whether you've succeeded or not. And that is slightly non-trivial to do, because like in earthquakes, there is no known method that works. So we don't actually have a comparison. And most of the methods you try are biased in various ways. So here's a picture of what earthquake data looks like. This is a region we are looking at in Southern California. It covers essentially all of the Los Angeles area. Here we have the desert to the top left, and we have the Pacific Ocean is around here. And Los Angeles is around here. And so you can see this striking spatial structure. That's because they're fault lines. The San Andreas fault is the most well-known, but there are lots and lots of faults. There are hundreds and hundreds of faults in Southern California. There are here 4 squares. That's because we looked in the initial analysis at 5 different earthquakes which occurred in this region, and this is just the spatial region which is of interest. All right, so now let's come to this slide here, which illustrates the data from 1950 on earthquakes to 2020. And this is pretty interesting. So here we have various things along the y-axis, and here we have our binning along the time axis. This comes from fortnightly binning, so there are roughly 26 bins for every year, and we have here whatever it is. We have 70 years, and then we compare various plots. So here is actually magnitude. It's pretty smooth. This is the yellow. It is the sum of the magnitude. You just sum up the magnitude of the events in each bin. Now that should be compared to the most dramatic, which is the purple. This purple, whereas this yellow thing has a tiny blip here, the purple has a huge blip. And the purple is not even energy, it's the square root of energy. If it did energy, the purple thing would go out off the roof. So this points out that if you plot energy versus time, it is highly spiky. And another thing we have, is not so easy to tell from this graph. Here is a blue line here, which is pretty spiky. The blue line is the multiplicity of events is the sum of the number of events in that space-time in the time region. This is the summed over space of events with magnitude greater than 3.29. And those events, that multiplicity is spiked roughly in a similar fashion to energy to the quarter. It has about the same height. And this thing here is what we will call energy average magnitude. It weights everything with the energy. When there are two magnitudes, it doesn't add the magnitude. It converts them to an energy, adds the energies, and then takes the log to make the total magnitude. And also by the way, there's some lines here which are the earthquakes, and so these spikes essentially all correspond to earthquakes. Significant earthquakes which are listed in the earthquake category as a magnitude 7.3, a magnitude 7.2, 7.1, and so on. So this really highlights the difference between choosing the log of the function versus the function. There's a huge difference in the shape. And we will come back to discuss what that means. So this is called choosing f of x. So this is important in all time series. And I used to ask people, what are the rules? What can I do? And the answer is almost always, you can do anything you like. Because deep learning just multiplies matrices and gets an answer. It doesn't care what the inputs and outputs are. Now, what does matter is how sensible all of that is. And let's sort of think about f. So I told you it's probably reasonable to make f monotonic. So as x increases, f increases. That seems reasonably reasonable. You should restrict yourself to that type of function. Although there's nothing in deep learning that says you have to. But when we think about what deep learning will do, it will take these inputs and it will multiply them by matrices. It will add them, so they'll be multiplied by weights, added together. So what does it mean to add magnitudes together? What does it mean to multiply a magnitude by a number? Well, in the world of energy, it means sort of nonsense. If you add two magnitudes, you're actually multiplying the energies, because the log of E1 times the log of E2 is the log of E1, E2. So it's not so, it's as a physics PhD, I find it non-intuitive. The use of magnitudes, even though that's what I am using at the moment, is not so obviously reasonable, because it corresponds in this deep learning network is actually multiplying the energies together, which is sort of interesting. But now we have another way which we realize we better do, so that's a case for using energy. But there is a case for using magnitudes or log of energies or some smoother function of the variable. Notice if you take an observable x and compare log of x with x to the 0.1, x to the 0.2, x to the 0.5, x to the 1, you will get more and more dynamic range as you increase the power of x. And log is the least minimum of the dynamic range. But it has a huge positive feature that the log compared to the energy, because the energy is unique, because in deep learning, you really need to keep the values in the range around 0 to 1, or negative, somewhere around that region, because the activation layer is acting on an absolute value that's around 1. So what's then the problem with energy? Well, if I chose the energy for earthquakes, then the typical earthquake energy compared to the I will have to divide. I need to make all my variables lie between 0 and 1, at least roughly. So I'm going to divide by the maximum earthquake energy, and that means the typical energy, earthquake energy, is 10 to the minus 5. Well, that's not terribly good. We have a problem formulated so its maximum is 1, and the The modal value is 10 to the minus 5. Well, that's not a very sensible use of the range between 0 and 1. Most of your data is between 0 and 10, plus or minus 10 to the minus 5. And there's just a few 1s and 0.5s and 0.1s and things like that. So there's an interesting conflict between sort of physics and numerics. And I have not seen that discussed, but I think it's there, that conflict. I think in general, the numerics is the right approach to make, because even though it's sort of, as a physicist, I don't like multiplying energies, I also don't like having this terrible dynamic range. It's very unlikely that the poor neural net can learn anything if it's all the action is in the tiny part of the phase space of numbers. Now I mentioned energy versus log of energy, but there is a case where the square root of where f of x equals the square root of x is a good choice. So what happens if I take the square root, if I take a set of observables and square root them? Well, again, that increases the dynamic range. Namely, it makes the points more spread out between 0. So I take x of x max and then take its square root. That spreads it out between 0 and 1. And so you're going to get a nicer distribution of numbers, which hopefully these matrices and weights and things can more easily disentangle and find truth from it. But actually, in the case of square root of x, in some cases, it's most natural, because you're going to use a loss function, which is goes like x. Well, according to counting rules, the error, if you have a number of events x, the error in that is square root of x. And so actually what you do want is the square root, because the square root has error of order 1, and the x has error of the square root of x. When we add the losses together, we want those losses to have equal weights. That will only be true if I take the square, if I take the square root. Now that will be a rigorous argument if COVID data had counting errors, but it has more than counting errors, so it may not be quite rigorous. But it still says, like in the program I have a choice between log, square root, or actually fourth root, not logarithm of the fourth root, the square root, and the natural value in my input code to try to choose the right function to get the best out of things. So here is a depressing plot. This just looks at those 5 earthquakes. This is what we did right at the beginning. And it just looks at the values of the blue is the count of the number of earthquakes, and the orange is the maximum magnitude, not the summed magnitude, the maximum, which is near actually the energy average magnitude tends to be the maximum, because the maximum always dominates if you weight by 10 to the 1.5 m. And if you look at these 5 plots for the 5 earthquakes, this is for the 2 years before the earthquake, there's no structure of any obvious uniformity or significance. So this is an important feature of earthquakes. There's nothing obviously going on. Now, if we look at, I think, here's one example of the, this is earthquake number 1. It's in this region here. And this has got the data in here. This is for the 2 years before the earthquake. And it's actually, this region here isn't nearly as intense in terms of earthquakes as the region up here, which doesn't have any major earthquakes occurring. And in fact, this region here has also got more action than this region here. So there's no obvious pattern that you can predict an earthquake from its previous structure. And this is, well, but now this is there was a large earthquake in about half a year before that particular event. But one thing that is true is that after the event, you have a huge number of aftershocks. So there's a huge peak in the number of events number of quakes seen. So, but that's not useful. We want to predict. We don't want to know that we had an earthquake. We want to predict there will be an earthquake. So aftershocks are not so useful. Well, I'm going to skip over this given the time. These are just the same thing for the other 5 earthquakes. I'll put up these slides. So this tells you how we did all this analysis. We always think about magnitude is the same thing as the log of the energy. And so the energy is 10 to the 1.5 times the magnitude, and we calculate energies. And so if we want to accumulate data in a bin, in our case, 14-day bin, we add all the events in that bin together, and then we form this quantity. We form the energy for each event by summing 10 to the 1.5 times the magnitude, and then we take the log on 1 over 1.5 times the log. And that's similar to maximum magnitude, as I explained. If we do other things, we also weight them with the energy. So we just multiply everything by 10 to the 1. We want to find the depth, the average depth. We take each depth, multiply the depth by 10 to the 1.5 times the magnitude, and then divide by the sum of 10 to the 1. So we get the average depth weighted by the energy. All right, so let's come back to some general rules. Well, so we have bad data. So let's look at bad data. All right, so I just took this from today's COVID data. If you go to the Johns Hopkins source about world number of cases, well, if you look at sometime around November 2020, there's a huge spike in the number of cases. It obviously, some country forgot to tell Johns Hopkins its data and added it all on one day or 1 week or whatever it was. And probably 1 day. And so this data here is just wrong. And quite how to deal with it is not so obvious, because you can include it, but it won't have any meaning, because it's really, this data here should be folded into the previous data. There is another interesting structure here, which is the ups and downs. This ups and downs is the weekly data. It's the weekly effect that the number of cases, and especially the number of fatalities, is undercounted on the weekends, and then that undercounting is made up during the week. So you get dips, especially on Sunday and Monday, and to a lesser extent Saturday, and Tuesday through Friday, and have the dominant recorded data. And then you can get rid of this by taking 7-day averages, but this is not done here. So anyway, you have some structure here, the wavy structure, which is real. That's an actual feature of the data. And you have bad data. And actually, if you look at here, here's worldometer. That doesn't have this spike. So obviously, worldometer recorded the data in a different fashion. That's another feature. I mean, if you look at, for instance, Johns Hopkins versus worldometer, there's a 5% difference in the counts between those two sources. They give everything to the nearest case, but they're off by, well, by now it's a huge number of cases. They're off by millions of cases worldwide. But that's because it's inevitable that different sources will give different counts. But the features that are the same. This shape and this shape are roughly the same shape. That's not what I meant to do. All right, so data is wrong, and also data is, and this actual feature of having wrong data, which you need to worry about, that's been true even before. That's not only with deep learning. That's true of all possible data. I mean, I've been analyzing data now for a long time, 50 years, or 55 years. And I always had that problem, because data has different reliability, or the amount of, in inverted commas, wrong data published is enormous. Although sometimes the wrong data has correct insights from it, because although the data may say have an incorrect overall normalization, the trend in the data may be correct. In any case, if you want to use data, you have to do a lot of cleanup. Now, if you look at the data, there are two types of data. One is those predictions I mentioned, which is often the same information when we're doing earthquakes. We're predicting the same things as we're inputting. But when we have predicted data, it's actually much easier to cope, because if you look at the loss function is the sum of the prediction, the observed value of a prediction minus the calculated value of the prediction. Well, if the observed value is bad, you just drop it. You have a huge number of, you have a sum of a lot of things in the loss function. You can drop some of them if the bad data is bad. So output data, you just drop it. Input data, you can't drop because the time series, formalism, and recurrent neural nets require the data all to exist. So you can interpolate, you can actually set up the neural net to learn the bad input, the missing input data, or you change the input formulation to avoid bad data. Like if the data is only bad for temperature, but is okay for rainfall, well, you just input rainfall. Another thing you have to do is to look at the data, is to choose which data to look at. Well, it's good to, like in the case of the Korean data with cities, you might want to use the sum over cities to judge the total predictive value of the system, but you want to feed in each city separately, because the more separate, we want to use big data, so the more separate time series you can look at, the better. And of course, this is big data, so we probably should try to use as much as possible. But there's also a question of practicality, especially if we're limited to CoLab. Like when I started off with 2,400 earthquake locations, which is the number I have in Southern California, I took a long time on CoLab. About a couple of months ago, I reduced it to 500 by just using, with advice from the earthquake expert, the locations with significant activity. And that was actually only 500 of those 2,400 cells. And you can see that from these pictures here. There's a lot of blank space here, but it's not so interesting to look here in the middle of the Pacific Ocean where nothing's ever been observed. So you just drop those cells. Whereas you want to keep all these ones up here, which got large counts. So we had 500. We got down to 500, and those might take 10 minutes an epoch to run on CoLab. Done that. Actually, so now why don't we turn to Baikuns? Let's stop here, which is looking at some of the results. And what's happening in the chat? All right. So now, Baikun, why don't we think about your problem? So you have, so I did one thing I didn't mention about input data. You want to input static and dynamic data. So you have, or you could just have dynamic data. In the case of COVID, we had lots of static data, which represented the health status of each of the counties. That the number of, there was a number called the percentage of people with asthma, or the percentage of people with who are 60 years old or more, and that data was a static piece of data which you fed into the LSTM just as the same value at each time. I mean, that's intuitively correct, because if you take Newton's law, we have static data, masses, and mass is important. And we're trying to write an operator which depends on the region, in the case here, a Korean city for Baikun, or a part of Southern California for my earthquakes. And we have static data and dynamic data. And we're trying to use the combination of the static and dynamic to predict usually the dynamic future. So Baikun, do you have any questions? Have I answered implicitly your questions? You need to take monthly data. You need to write a deep learning network which takes a time series of maybe, I don't know, 5 months in a row. That's probably a reasonable number. And you run that time series of length 5 through the deep recurrent neural net, and you predict the whatever you want to predict, which may be some resource need in the following month, and you should feed in all monthly data you have, and you would have then the number of time series you have would be 48 minus 5, which is probably, you might have it's either 42 or 43 time sequences if you made the length 5, and nine cities. So you'd have 9 times 42. And each of those time series would have every one of those monthly values assigned to it. So you're still muted, Baikun. Can you? Does that answer your question?
Yes. Actually, as I sent the mail to you, I had the supply amount of data and climate and oil and coal price.
Yeah, but all of those are relevant.
Yeah.
You just feed them in. You assign it to each city and feed it in. If it happens to be the same for each city, that's okay. Almost anything's allowed in these networks. It's actually much better than some of these older methods, because you can do almost anything. And also, because you're using steepest descent, in the older methods, you would tend to run into trouble because you would get divergent answers, but you don't get divergent answers with steepest descent. Steepest descent always goes downhill. It's not taking derivatives or anything, so it's not sensitive to misdefined, poorly defined values or anything. Hopefully it will run downhill and find a solution, even if it's not even if there are some ambiguities, because it doesn't matter. The older optimization methods, which use Newton's method and things like that, they never worked if you had too many parameters, because you then got negative. You got lots of zero derivatives, but zero derivatives of particular parameters doesn't matter for deep learning. So I would expect you to be able to get reasonable answers.
When you look at the examples that you find on the network, on the internet, you find sometimes different time scales. There is, for example, a very elaborate example about energy and those things that looks at the use of energy per week, for example, making it classifying it by day. How much do you use on Sunday or on Monday or on Tuesday? And the examples in this one are then agglomerated over that particular day. There are other examples where you do the prediction for the entire year, where you put seasonal data. So you can take a look at these examples, and you at one point need to be making a decision of what time scale you would like to use at that largely depends on your input data.
Okay.
What you have. So in some cases, you know, the energy consumption in 1970 was quite different from the energy consumption in 2000. Think about also events that took place that are completely out of the control of the weather, where you know you can put in any kind of weather, but it has no impact on the consumption. If you, for example, think about back on the oil crisis that happened a long time ago, and so you need to identify a proper time scale for your data.
Of course, you could do you could have a variable which measured the extent of the current crisis, and which you just increase when there was a oil crisis. I mean, at least in principle, that could work. In this earthquake data, the input data I had was data averaged over a 2-week period. But what I predicted was 2 weeks, 4 weeks, 8 weeks, 6 months, 1 year, 2 years, 4 years. So I predicted a wide range of time intervals, varying from 2 weeks to 4 years. But the input was always 2 weeks. And as far as I know, there is no reason why the output time period cannot be totally different from the input time period. As I said, there aren't rules for. The only rule for deep learning is, does it work, or does it give sensible answers? As long as you can, because it's plausible that the time series has implications for the data over the next average over the next 4 years. So it's perfectly reasonable to try to predict that wide range of time intervals. Of course, you're going to get poorer results than over the possibly, but actually, even if you take earthquakes, the big earthquakes is what you care about. They're probably, nature probably has year-long uncertainties over when they're actually going to occur, because of the fact that these are phase transitions means they might occur in quite strikingly, they can be delayed by very tiny effects. So it's very difficult actually to give a precise prediction of when an earthquake is. It's more plausible that you'll be able to predict there will be a significant earthquake in the next few years. But all of these are very domain specific, and you need to basically adjust your, you need to make reasonable decisions. But my impression is, for your data, it shouldn't be too difficult. If you have any trouble, just give me an email. I think you just make monthly, you should send me an email with the date. Let's assume we have 4 year time interval. We choose the number of, we have monthly data, so we choose the number of months in our actual sequence for the recurrent neural net. And naively, something around 4 to 6 should be reasonable. If it's much longer than that, you're going to use up all the data. So and I've got reasonable answers on some other problems with 5-week time series, 5 time series of length 5. And then you just need to tell me what the input is, what each input sequence has, and then what the predictions are. And we're trying to train a neural net that applies to all Korean cities. It's the same net for each city. So you train it on you just join all your time series together and you run it through. And then you either distinguish cities by the input data, because you're inputting the sequences. That's one way of telling the city apart. Or it's possible there are some other variables you have which distinguish cities. In the case of earthquakes, the only thing that there was one static data fed in, which was which fault the particular location was on. We divided Southern California up into fault regions and assigned every location to a fault region. That's the only static data we had, which is significant because you expect events on a particular fault to be correlated. But we have no other static data. For COVID, we had a huge amount of static data because of all the medical signatures were static. Some was dynamic. The amount of social distancing was a function of time. So that's some sort of medical signal, which was dynamic. So that was a time series. But the percentage of seniors was a static variable. So I think you should think about if you have any static variables for distinguishing the cities, and they can be sort of interesting static variables. A flag to say if the city's on the coast, or whatever characteristic, or the city is high up in the sky. It has a high elevation, or what. Maybe I don't know whether Korea has high elevation cities. Maybe not. I don't remember a lot of mountains in Korea. Anyway, you're allowed to choose those static variables. And that are I say, in the Newton's laws, they are equivalent of giving and representing the mass of each city in some sense. The static variables which are used to formulate in the dynamic operator which distinguish the different operators between the cities. And then those static variables can help the net learn different cities more effectively. Anyway, Bakun, just send me a message if you have any further questions.
Okay, thank you.
Any other questions? All right, so next week I will continue this. I will continue this discussion, and also, if you have any problems at all in getting your thing formulated, tell us, because we might still be able to correct it if you tell us next week. And after that, we're nearing the end of the semester. Okay, so thank you very much.
Thank you.
Thank you.